Hello, we're going to work a couple problems, I think 5 from chapter 14. So if you've already listened to the lecture on chapter 14, you realize that it's just a special example of what we learned in chapter 13. So we're still focused on equilibrium. When a system comes to equilibrium, what concentrations of reactants and products you have. And the new things in chapter 14 for us really are just an understanding of what acids and bases are. So I am going to plug this in. Okay, so the first one we're going to look at is problem 1449, and I won't do all of them. Once you do one, it's pretty clear what's going on. So if you look at the problem in the text, it says for each of the following reactions, identify the Bronsted-Lowry acids and bases and their conjugate acid-base pairs. So the first reaction is the cyanide anion reacting in water to make HCN and OH minus. So in this case, the CN minus, the cyanide, is acting as a base because it's pulling a proton off of water. So in water, it is creating OH minus. So it's picking up the proton. The water is giving up the proton, so it's an acid. So the conjugate acid-base pairs are the water is the acid, the OH minus is the base in one pair, the cyanide is the base, and HCN is the acid in the other pair. So the second one, B, is an example of a triprotic acid, phosphoric acid. So once you've taken one proton off, this can still continue to act like an acid. So H2PO4 minus could act as a base, but in this case, because it's reacting with water to make H3O plus and the anion from this guy with one less proton, this is a base. So it's acting as an acid in this situation. So it's giving up a proton to water. Water is acting as a base. Water is becoming hydronium, and the H2PO4 minus is losing one proton just to become HPO4 2 minus. So the acid-base conjugate pairs, this is the acid, this is the base, water's the base, and hydronium is the acid in that pair. You have another situation here, it's not a water reaction, it's a reaction of NH4 plus with nitride. No? Can't remember the name of this. Nitrate has 3, nitride is nitrogen minus, so I slipped my mind for a second. So this is acting as an acid because it's giving a proton to this anion. When that picks up a proton, it's becoming an acid, and when this gave up a proton, it's becoming a base. So you have ammonium and ammonia as an acid-base conjugate pair, and the NO3 minus is acting as a base, picking up a proton to become the acid in that conjugate pair. So that's just some new definitions for us. What are acids and bases, and how do those reactions take place? So the next problem that we're going to do, I'll have to move that up in a second. I don't know if you can hear my cat. He's mad that I locked him out of the room, but he'll like to get on top of the computer. So he can't come to class anymore. So the next one we're going to do is 1461. This one is on page 581. Notice I'm always picking the odd numbers. The odd numbers don't have answers in the back. The evens do, and most of those have been assigned as homework for you. So these should help you do the one that's very similar, which would be 1460. So in this problem, they want us to calculate the H3O plus, the hydronium ion concentration, given we have the pH. They want us to do it with the right number of sig figs. So if this is the pH, remember the number of digits to the right of the decimal tell you the number of sig figs total that would have been in the concentration. So if pH equals negative log of hydronium ion concentration, take the negative to the other side. And then in order to get rid of the log, if you raise 10 to the log, these are inverse functions, so they cancel each other. So 10 to the minus pH is going to give you the hydronium ion concentration. So for A, it gives us a pH of 9.0. So it's going to be 10 to the minus 9. The hydronium ion concentration, so 1, we only have 1 sig fig because 1 digit to the right of the decimal. So 1 times 10 to the minus 9 is the concentration of the hydronium ion in molarity. The next one, 7, with 2 zeros to the right of the decimal, means we have 2 sig figs. So 10 to the minus pH gives us 1.0 times 10 to the minus 7. So very similar to problem A, just have 1 more sig fig. The next one is a pH of negative 0.3, and that's a very, very high hydrogen ion or hydronium ion concentration. Has only 1 sig fig. The 3 is the only sig fig we have. So if I change the sign, 10 to the 0.3 equals 1.995, but I only have 1 sig fig, so that's a 2 molar concentration of H3O+. The next one is a pH of 15.18. I feel like something is wrong with that. That one can't be right. It has to be a solution that's basic. So I'll have you check that one, but we should have a very, very low H3O+ concentration. 10 to the minus 15 should not be 6.6. I guess I do have my calculator right here. I'll just redo that really quick. Yeah, I forgot the times 10 to the minus 16. So wouldn't make sense that a solution with such a high pH. High pH means a very low concentration. So the right answer is 6.6 times 10 to the minus 16 molar. We have 2 sig figs because we had 2 digits to the right of the decimal. So hopefully you can see that. Okay. So the next one that we'll look at is 14.67. It's on the same page, so it's on page 581. And it just wants you to calculate, let's see, the pH of these following solutions. So the only one that's a little bit tricky might be A. A gives you a solution of an oxide, sodium oxide. And on page 550, they talk about how oxides are really bases. So this is one you might want to write on your note card, what these two reactions are, because it'd be easy to forget. So they tell us that we put in 0.2 grams of the sodium oxide and make a total solution of 100 milliliters, and what's the pH? So the sodium oxide is soluble, but when oxide is dissolved in water, it's not stable. So it reacts with water, picks a proton up to make OH minus, and then to leave the water with just OH minus. So for each oxide, you get 2 OH minuses, you get 2 base molecules. So if we use the molar mass, which I got from Wolfram Alpha, and convert it into moles of sodium oxide, then the moles of sodium oxide I have to convert into moles of OH minus. There are 2 for every 1 mole. So I have 6.4 times 10 to the minus 3 moles of OH minus in there. It's present in 100 milliliters. So that gives us a concentration of 0.064 molar in OH minus. So to calculate the pH of that, we have to first take the OH minus concentration and change it into H3O plus. So you remember you do that by doing Kw over OH minus. So 1.0 times 10 to the minus 14 divided by 0.064 gives us an H3O plus concentration of 1.5 times 10 to the minus 13. So if I take the negative log of that, it'll have 2 sig figs to the right of the decimal. The pH is 12.81. Very basic. The next one, B in that problem, says you dissolve 1.26 grams of nitric acid and you make a solution that has a total volume of 1/2 of a liter. So the way that you would remember that nitric acid is a strong acid and that you don't have to deal with an equilibrium is because if you look in Appendix C, which is the table of Ka values, you won't find nitric acid. And so my rule would be if I give you something on the test, if it's not in your Ka table value, then you should assume that it's a strong acid or a strong base. So they're not there, or this isn't there, so we'll assume it's strong. So that means we get the number of moles of nitric acid, divide it by the volume of the solution, and we have a concentration of 0.0400. If it's a strong acid, remember from the lecture, I'm going to put a single arrow, reacts forward. None of the H3O plus goes back. It's not an equilibrium. It all dissociates to make H3O plus. So that means the H3O plus hydronium ion concentration is equal to how much nitric acid you put in. So then it's simple. The pH is just 10 to the minus the hydronium ion concentration. We have 3 sig figs in the molarity. So we have 3 digits to the right of the decimal. So I got 1.399 as the pH of that solution. Okay, so there are 2 more in there, but they're very, very similar. So when you do 1466, I think you'll have the idea from what I just showed you. 1475 is on page 582. This is one where you're taking aspirin, and each tablet, it says, is 324 milligrams of salicylic acid, which is the active acid in aspirin. It's a weak acid, and it's a monoprotic weak acid, so there's 1 proton that comes off as an acidic proton. The Ka is pretty big, 10 to the minus 4. So the problem tells us that we dissolve 2 tablets to make a total volume of 300 milliliters. What's the pH and what's the percent dissociation? So they give you the formula. So I use Wolfram alpha to get the molecular mass. So 324 milligrams times changing it to grams times changing it to moles. And you know what I forgot to do was multiply by 2. So everything here is going to have to be multiplied by 2. So this is going to be 12 times 10 to the minus 3. And I would have to go back to Mathematica. I think that's how I did this because it's pretty dissociated because it's such a large Ka value. Let's just go ahead and do that quickly. I'll plug it back in. So in Mathematica, whoops, capital S for solve. And we're solving the same equation except this is a 12. So we're solving x squared divided by 0.012 minus x equals 0.0004. I could put it in as an exponent. It's just faster to do it that way. Whoops, not 4, 3. Yes, and then we're solving for x. And I do shift return. And now my x value is 0.0016. We only have 2 sig figs because of the Ka. So rather than 1, 2, this is 1, 6. And so when I take the pH, let's see what we get. Let me do that again, 0.016 log. Yeah, so it's just a little bit different. We haven't changed the order of magnitude with such a small change. So our pH is now 2.80. And if we look at the percent dissociation, whoops, I've got to go back to my screen. Sorry. It's very easy at this point to forget. Okay, so I come back here and I put 6 in here, which gives me 2.8, so 0.0016. And then the percent dissociation is how much dissociated, so x is the amount that dissociated, divided by how much you started with. So if I take that ratio, it is and I get 13%. Okay, so that was 1475 with the corrections because I forgot that it wasn't 1 tablet, it was 2 tablets. So this is actually a good point to think about when you're taking a test. And if you have extra time at the end, rather than just working through what you already did, if you actually redo what you did, you'll often catch mistakes like this. But even just reworking it and looking at it, if you've written it out clearly, if I hadn't written this here from the problem, I wouldn't have caught that error. So hopefully on the test, you'll always have enough time to at least relook at each problem. So the next one deals with a polyprotic acid. So it's 79 on page 582. And so it tells us that we have this acid, which is sulfurous acid. It's not a strong acid, but it is a diprotic acid. In the problem, they give you 2 Kas, which would be the hint. Also, if you're looking in the Ka table, it would give you 2 Kas. So if they weren't given in the problem, you'd still know that. So I said in the lecture that it's the first dissociation that will have the biggest impact on the pH and will determine the H3O plus concentration. We're just going to confirm that here. So in this problem, they want us to give the concentrations of everything that would be in the solution. So hydronium, the deprotonated acid, the acid not deprotonated, the conjugate base after you've taken off the second acid, and then the base, which is always present in water. So when we look at the first Ka, 1.5 times 10 to the minus 2, that's a fairly big Ka. So if our concentration of the acid that we put in is 0.025, some of that will dissociate, which will create some of each of these. When we plug that into the Ka, we get an X of 0.013. So I am going to assume, but I'll confirm that my assumption was valid, that the H3O plus concentration is 0.013, the HSO3 minus is 0.013, and the H2SO3 is what we started with, minus how much dissociated, quite a bit dissociated because this is so big. And so we're left with 0.012. How does the second Ka impact this? So this is something you have to think about a little bit from chapter 13, Le Chatelet's principle. So when the second proton is going to come off, we start with, how come I keep making mistakes? No, I didn't. So we start with the concentration of HSO3 minus from the previous dissociation, but some of that might dissociate in the second reaction. That will make some of the conjugate base, but this won't also be X. This will be how much H3O plus is in the solution from the first dissociation, plus how much comes into solution from the second dissociation. So this is essentially Le Chatelet's principle. If we have some H3O plus in this solution, this reaction won't go as far forward. Still use the same logic. So Ka2 is equal to X, the concentration of SO3 2 minus, times the concentration of hydronium, which is 0.013 plus X, divided by the concentration of HSO3 minus. And when you do this, you can do it really easily because this is really small. This is a very small Ka. So the way I solved this problem was I said X is small relative to 0.013. So then 0.013 over 0.013 is 1. And so X is really equal to Ka2, if you notice. And then when you think about that, X is the amount of H3O plus that was added to the solution by the second dissociation. Now I can go back and confirm that that's a good assumption that all the H3O comes from the first dissociation. So if I went back up here and if I added 0.013 and X, would X change if I added 6.3 times 10 to the minus 8? No, wouldn't be significant. We would round it to 0.013. So it was valid assumption, and it will be in all the problems you do. The first Ka is much bigger always than the second, so it's the first one that will determine the H3O plus concentration. So then the SO3 2 minus is the X concentration. OH minus is Kw divided by the H3O plus concentration. And did I ever do the pH? They always ask you for the pH. I didn't do the pH, so I'll do the pH really quickly, 0.013. So the pH, which will have 2 sig figs, is 1.89. So that's a good one to think about making assumptions and also reminding us of things we know from chapter 13. If we already have some H3O plus in the solution, then this won't just be X. We'll have to add that to it. And it is a valid assumption to say that the first proton coming off, so the first equilibrium is the one that will impact the pH. The second one is usually insignificant relative to the first one. Okay, so the next one is a KB problem on page, it's number 87. It's also on page 582. So if we read it together, page 582, 87. It is morpholine. They give us the formula. It's a weak base. They give us the pKb of 5.68. They want us to calculate the pH and the concentration of everything in solution. So for a weak base dissociating in water, it's the base plus water goes to the conjugate acid plus OH minus. A pKb is just like a pH, the P function is always the negative log. So if I want the KB, I go 10 to the minus PKB, and I get a KB of 2.1 times 10 to the minus 6. So this really isn't a very strong weak base. Solve it looking at the equilibrium. So it'll be x times x divided by 0.0100 minus x, because water is a liquid. And so when I solved this in Mathematica, I got 0.00014. And even though my concentration had 3 sig figs, most of the Kas and Kbs that you have are only going to have 2. And I only have 2 in this one because remember, it was determined by how many digits were to the right of the decimal. It tells us the total number of sig figs here. So this means that the concentration of the conjugate acid and the OH minus are equal to X. The concentration of the base that remains is what I started with, minus X. So I end up with 0.0099. And that only can have 4 digits to the right of the decimal because of subtraction. So even though this had 5, I don't know the 5th one here, so it has to be rounded to 4. The H3O plus concentration is Kw over OH minus. So I get 7.1 times 10 to the minus 11. That gives us a pH of 10.15. So a very basic solution. 2 sig figs to the right of the decimal because of 2 sig figs in the number. So the very last problem we'll look at is one where you look at dissolving a salt and you ask the question, will the solution be acidic, basic, or neutral? So you have that table, I think it was on page 450. Let me just confirm that. Let me find it then. It is on page 570, the table that is useful. But you can also think them through. So when we dissolve barium nitrate, you can think of nitrate as being the conjugate base of HNO3, which is a strong acid. If you say it's a strong acid, that means it completely dissociates in water. So it's not going to react backwards, which means NO3 minus isn't going to pick up a proton and act like a base. So this guy's neutral. Barium you can think of as the conjugate acid of barium hydroxide. If you dissolve barium hydroxide, it's a one-way street. All of it dissociates, which means barium is not going to pick up OH minus and make the solution acidic. So each of those is neutral, so the overall solution is neutral. So you can think it through that way, and you can also use the table on page 570, which just summarizes that idea into rules. So this one, NaOCl, this is similar to the barium argument. That's going to be neutral because it's a conjugate acid or the anion from a strong base. But if we look in our Ka table, we will find the acid in the Ka table. So if HOCl is a weak acid, then OCl minus is a weak base. So when you put this in water, it will be in equilibrium to make OH minus. So that makes this whole solution slightly basic because this one was neutral. Excuse me. So the last couple here, ammonium iodide. If we look at this guy, it's a weak acid. The reason I know it's a weak acid is because NH3 is in the Kb table. So if NH3 is a weak base, then if it picks up a proton, that conjugate acid is a weak acid. So this contributes acidity. This is a strong acid. So if iodine's in solution, it's not going to react backwards. to make the solution basic by picking up protons. So this guy will be neutral, making the entire solution acidic because of the NH4+. E is a little bit harder because NH4+ is a weak acid, NO2- is a weak base. So we find NH3 in the KB table. We find HNO2 in Ka table. And so we need to know the Ka for this and the Kb for this. And we have the opposite. We have the Ka for the one that's a base and the Kb for the one that's an acid. So we have to take each of those and we have to calculate the opposite. So if I want the Ka for NH4+, so this says the Ka for NH4+, it's going to be Kw over the Kb for NH3. So it gives me a Ka of 5.5 times 10 to the minus 10. The Kb for NO2- is going to be Kw over Ka for HNO2. And the value I get is 2.2 times 10 to the minus 11. So when I look at these two ions, the Ka for the weak acid is greater than the Kb for the weak base. So that means the solution is going to end up slightly acidic, even though you have an acid and a base in there. So those ones sometimes are a little bit challenging because you're new to the ideas of acids and bases, and then understanding how when you have something in solution, you want to look at it and compare it to what acids and bases it's representing. So that table on page 570 is helpful. And as you get more familiar, chapter 15 is going to be another chapter that mostly does weak acid base equilibrium. So we'll look at this a whole bunch more in another chapter, so you'll get even more familiar. So that is it for the problems for chapter 14.